All right, I'm going to introduce you guys to exponential growth and decay, and what we're going to do is we're going to use that skill of factoring by grouping to kind of generate the formula that we're going to use from now on for exponential growth and decay. So if you cannot do what we're about to do in example A, that's okay. You need to be able to do what we do in example B. But the stuff we do in example A is going to build the foundation for what we do in example B. I can just tell you that if you're able to do A, you'll have the opportunity to earn some bonus points in the future. So do your best to try to figure out how we can do a problem like A. So it says that James owns a chain of restaurants that operated 200 stores in the year 2000. The rate of increase is 10% annually. So that word annually just means every year, right? So each year, this number of stores increases by 10%. How many stores does the restaurant operate in the year 2007? So a couple things we got to pick apart first. 10% is the same as multiplying something by 0.1, right? A percentage is just a number out of 100. So 10% is the same as 1 out of 100, and that equals 0.1. So if you want to turn that percentage into a decimal, just divide that number by 100. There it is. So we're going to start off by making a table here. We're going to have whatever year it is. And we're going to have the number of stores. And we're just going to go year by year and kind of figure out how many stores there are each year. So in the year 2000, this is our easy year, he's got 200 stores. Easy. But in the year 2001, he gets 10% more. So he had 200 stores. Those are still there. But we're going to add to that 10% of 200. So to be clear, this is the stores that already existed the previous year. This is how many he gained. He gained 10% of 200. So we have the original 200 plus the new 10%. That's how many stores there are now. Now this is going to start getting really complicated if we do this year after year. So what we can do is we can make this look a lot nicer by grouping. What do these two things have in common? Well, they both have a 200. So I can factor out a 200. And on the inside, I'll have 1 plus 0.1. And I could even then take it one step further and say, that's the same as 200 times 1.1. So that's how many stores he had in the year 2001. He had 200 times 1.1 stores. The year after that, he still has those 200 times 1.1 stores. He's still got the same number of stores from the year before, but he's going to add another 10% of that on top of that. So let me walk through this, because it gets a little bit hairy. The previous year, he ended with this many stores. So he still has those stores. But don't forget, he's going to gain another 10% each year. So he's going to gain 10% of what he has and add that on to what he has or had the previous year. So it's starting to get a little bit cluttered. But I can factor all this by grouping and make it look a lot nicer. There is a 200 times 1.1 in each of these terms. So I can factor out a 200 times 1.1, and that's going to leave me with 1 plus 0.1, which is 200 times 1.1 times 1.1. And notice that these two things are the same, so I could rewrite this then as 200 times 1.1 squared. So that's how many stores he has in the year 2002. And then we're going to take that to the year 2003. In the year 2003, he still has this many stores. That's how many he's accumulated up to this point. But he's going to get 10% more added on to that. So he's going to have 200 times 1.1 squared times 0.1. That's going to get added on. Here's your 10% being added in the year 2003. If I factor this by grouping, I'll recognize that I have a 200 times 1.1 squared in each of these. So I'll have 200 times 1.1 squared, and then I'll have a 1 plus 0.1 left over, which is going to become 200 times 1.1 cubed. And you're starting to notice something that's happening as we go along. In the year 2000, 0 years had passed. But in the year 2001, 1 year has passed. In the year 2002, 2 years have passed. In the year 2003, 3 years have passed. And you'll notice that as you move, the exponent of the expression goes up with the years. So this is the pattern that we're going to start to recognize. Now we could keep doing this all the way to the year 2007. But we're just going to keep getting this same expression. The difference is the exponent that we raise our 1.12. So in the year 2007, yes, we're just going to have this expression, 200 times 1.1 to the 7th power. If I punch that into my calculator, I get 389.74, roughly. We're talking about stores, though. I want to know how many stores he has. I cannot say he has 0.74 stores, so I have to round. And this is where it gets a little bit interesting, because normally here, you would turn this into 390, but you're not going to do that here. What he has exactly is 389.74 stores. 0.74 can't count because he can't have 0.74 of a store. It doesn't count yet until it's a full store. So what he actually has in this year is 389 stores. And it's important that you round in this way. It's kind of a different way of rounding because we're talking about a real world situation. You can't have 0.74 stores, and we can't round up. We can't say he's got 390 stores because that's just not true. He doesn't have that many yet. So you have to say 389 stores. So again, like I said, this whole thing, you may have the opportunity to show me you know this in the future for some bonus points, but this is not something you need to be able to do. What you need to be able to do is say, what have we learned from this? Well, we've learned that we've got a formula for exponential growth and decay. We can say that the total amount, or whatever we're going to end up with, is going to be equal to the initial amount, we'll call that the principal amount, times 1 plus or minus the rate to the power of however much time is passing. So let me label those real quick. So you might want to take a second and pause the video and write down those. So what we're going to do here in B is I'm just going to show you what you do need to be able to do. You need to be able to take this type of word problem and put it into that function. So we've got an attendance at a basketball game, and it's declining. That's really important because we're not growing, we're decaying now. At a rate of 5%, all right, I'm already thinking 5% means 0.05. That's going to be useful per game throughout a losing season. If there were 23,500 people, well, that's going to be my initial amount at the first game, identify the exponential function that models the attendance of fans from game to game. So we're not going to get a number because we don't know how much time has passed. We don't know how many fans we've ended up with. So what we've got here is that the total amount of fans is going to equal the principal amount, right? The principal amount is 23,500 times 1 plus or minus. Well, we're talking about decay here, so we're going to use a subtraction sign. The rate to the t power. We don't know how much time has passed. So at the end of this, I would say you should rewrite it as 23,500 times 0.95 to the t power. Now, all we'd have to do now is have them extend it and say 3 games pass, and then you'd be able to figure out how many people were there by just plugging in a 3 for t. Or we could say, now there are 21,000 people, how much time has passed? And you could plug in 21,000 for A and solve for t. right? So there's a lot of different things we could do from here. But all I need you to be able to do at this point is use this formula effectively. Again, if you can do all this and prove that formula, it will be useful, but it's not the most important thing in the world. All right? So we're going to practice some of this tomorrow, some word problems a lot like this, setting them up and solving them. Hopefully this makes sense to you. I'll see you guys tomorrow.